Hi, everyone. Good morning, good afternoon, good evening, wherever you are. Welcome back to Between Two Nerds in Hex, obviously. We are going to continue our discussion about BGP Convergence. I'm happy to welcome Jeff, my esteemed colleague and longtime
Morning,
friend.
Jeff.
Morning, Jeff. So we are going to do a short recap of what we have discussed in two previous meetings and then move to continue where we stopped last time.
Mostly because we can't remember where we stopped last time, I think.
Yeah, it has to do with age probably, but
we're also going to spend a little bit more time this time. We'll try to do a 30-minute session. As in the very first session, I mentioned that a friend of mine, a Facebook friend of mine, Eddie Chan, had asked, well, what about BGP convergence? And we thought it was a great question. And here we are 3 sessions along, still talking about BGP convergence. So hopefully with 30 minutes, we can finally wrap this up and maybe get on to something else.
So we've started with importance of ISN allocation scheme in leaf-spine topologies. The goals are use built-in into BGP's path loop detection and prevention, no path hunting. So when link or node fails, there should be only one path to that. And free-value routing, what it really means that there's no reflection of routes. So if you look at the picture, you don't want your spines to reflect routes back to leaves who will reflect routes back to other leaves. It results in inconsistent routing tables, and even if you just do basic monitoring and you happen to restart BGP session, depending on the order BGP peers come up, your routing table is going to look different. So it's really bad thing for monitoring. You don't know what to expect. It's absolutely unpredictable, and different vendors behave differently. So hopefully we convinced you to use a ISN allocation scheme where every leaf has its own ISN, all spines in the pod share ISN, and all super spines share ISN. What it gives you ability to stop routes, because when you reflect route back to spine layer, it sees its own ISN and blocks. When you reflect routes to super spine layer, it sees itself in the AS path, it's a loop, hence it blocks. So fast convergence, no inconsistencies, no path hunting, and automation. One might say, you need to configure more stuff. I think automation finally got there, right? It shouldn't be a problem for configuring different ISNs through machine-to-machine interface. So we are going to move to the BGP convergence topic. Short recap here. We are going to use exactly the same topology. So it's evenly applicable to 3-stage. So imagine there are no super spines in a single pod. It's not really different. So what we discussed last time was detection failure as soon as possible. So detection failure is a very important part of total end-to-end convergence. The longer you wait, or the longer it takes to detect a failure, the longer your convergence is going to take. The longer you're going to black hole to drop traffic, the longer you are not going to know that something bad has happened. So what we are saying here, in leaf-spine topology data center in general, you can often rely on loss of signal, loss of light. It's really good to run BFD because sometimes your link is still up. It's just IP stack that isn't working. BFD gives you validation at IP layer. So when your BFD is down, you cannot communicate at layer 3. What's also important is to make sure that your BGP implementation supports next hop tracking. If we take iOS, or for this matter, any old stacks many years ago, it would run BGP Walker once in 30 seconds, and in between, you wouldn't know. So if something goes away, you would still need to wait 30 seconds. or 60, actually, I don't remember anymore. So those days, usually when there is a next hop, BGP actually register to presence this next hop in RIP, and if it disappears, it reacts immediately. When you run BFD, in good implementation, you'll have registration to BFD state. So not the prefix itself, but the BFD as a protocol. So if BFD state on particular interface changes, so goes from up to down, you can invalidate all the routes immediately. It gives you very fast reaction on the failure.
Mm-hmm.
And again, if we look at even merchant low-end silicon today can do BFD at 10 milliseconds. Some can do 3 milliseconds. So you can do it really fast. You don't rely on TCP. You don't rely on BGP hellos. You really want to detect data plane failure, so link down. You want to detect IP stack failure, BFD down as soon as possible.
I've got a question on that. One of the, for BGP in the data center, one of the typical recommendations you get is to set the hold and keep alive timers a lot lower than what they usually come by default. Keep alive timers, usually might be 30 seconds or 60 seconds or something like that, and then the whole time is 3 times whatever that is. And you'll hear a lot of recommendations to crank the hold timer down to like 3 seconds, which makes the keep alive timer down to 3 seconds, which makes the hold timer 9 seconds, 3 times longer. And if BFD is tied into the BGP process, is that really necessary?
Absolutely not.
Do you really gain anything from that?
No, and the important point, BFD normally runs directly from the silicon. So every silicon has an OEM block that generates fast hello. So BFD, CFM, anything that should go at millisecond granularity. BGP hellos are sent from your switch CPU. So if you send too many and too often, you're actually overwhelming your CPU for no reason. You're not going to wait for BGP to fail anyway. And if you do, you have another set of problems. Yeah. So don't go too fast. It makes no sense.
Cool. The kind of going to timers and maybe to the next bullet that you've got on your slide here is MRAI timers, minimum route advertisement interval timers. I can never remember what acronyms stand for, but it's basically neighbor updates. And BGP obviously is designed for the internet, where it's a good idea to trade some convergence time for stability. And so you'll find neighbor update timers, MRAIs timers that will wait 30 seconds if something changes before sending an update. So maybe if there's instabilities in an internet network, it's collecting a lot of those instabilities that can all go out, in one update to a neighbor. Makes sense in the internet. In the data center, it doesn't, and so that's an important timer to set, or to change. If the default is not already at 0, set your neighbor update interval timer to 0, so that as soon as something changes, the neighbors are updated.
The recommendation for MRI timer in data center deployment is 0. Yeah. You update your peers as soon as possible, as soon as you know.
Mm-hmm. And then there's another timer. There's four timers. We talked about MRAI. I wish I could say that. And then hold and keep alive timers. There's also the connect timer that says, and again, this is because BGP is originally designed for the internet, and you want to trade some convergence time for stability. So this says if you lose a session, wait 60, I believe it's 60 seconds is the default usually. Probably varies from vendor to vendor before you try to send a go into the connect state again. And that's another timer. It's a good idea to reduce that timer, because again, in a data center, you do care more about speed than you do about. Well, I don't know. Maybe that's the wrong thing to say. Is to say we don't care about stability. Obviously, we do, but there's not the stability vulnerabilities in a data center that there are in an internet network. So setting the connect time lower is also a good recommendation.
Yeah, and your blast radius is really your data center. You don't need to wait for internet to reconverge. Yeah. So next, an interesting topic is how do you propagate updates? Data center is somewhat different than internet topologies. So there are two things. Number one, we would like to send an update to everybody at the same time. So if you're at spine layer here, you would like to update all super spine at the same time. You don't want what we call update dispersion. So most implementations today will do the job for you. So you don't need to configure explicitly peer groups in background. When update is exactly the same, your implementation is going to group them and send to everybody. However, if you configure different outbound policies, they are not going to be grouped. So make sure when you update one layer from another layer, your update policies are the same. So your implementation has the ability to group and send single update to everybody at the same time. So there's no dispersion.
Yeah, I think Cisco calls that dynamic peer updates or dynamic peer group updates or something like that.
Because, most people would still configure peer differently, and you'll end up with really dispersion and all the instabilities that came from the fact that another layer receives updates at different times and then start updating layers that is connected to it at different times as well. You don't want this. You want it to be as streamlined as possible. Another interesting topic, if we look at internet, what usually happens when you lose a route? You will install, probably you don't have another route because somewhere downstream to you, someone has already run best path selection and didn't select it. So you would really need to wait for route to come back and wait for propagation. In data centers, we almost always have more than one route, right? So if you look at spine, super spine layer, there are more than one way to reach, and this is the beauty of ECMP. However, what happens on route disappearing is important. Since now we have no single route, but ECMP group, every ECMP group has an ECMP head that is the next hop that's going to be sent in update to another layer. So since you didn't lose the path, it just has changed, two things are happening. If the next hop you lost is the head of a ECMP group, you're going to send an explicit withdrawal. If it's still there, there's not going to be any update because reachability is still there, next hop is still reachable and valid. So if you look at large deployments with many routes, it gives a great degree of stability because you don't even need to notify underlying layer about any changes. The reachability is still there, next hop is still valid. The fact that particular next hop has disappeared has only affected you, your layer, and the way you're going to ECMP the traffic. So important point to know, the convergence in this kind of topologies is much faster due to the fact that routes are grouped in ECMP groups.
And it's kind of, that's an interesting kind of leading topic for maybe another session on ECMP. There's so much to say around that. And just as one example, we've sort of been talking about convergence time, but convergence accuracy is also extremely important. And just one example of where you might need to adjust BGP behavior in a data center is just looking at Jeff's diagram here. And we don't have this illustrated, but let's say there is a server on the lower left that is multi-homed to the two leaf switches AS 65004 and 65005. And it's sending some prefix A. When that gets to the two spine switches at AS 65001, they see two different different AS paths for prefix A. One of them is coming from 65004 and the other is coming from 65005. The AS paths lengths are equal, but default BGP rules say even though they're equal, they're not the same, so just pick one. And you don't have multipathing. There is a command you can use, and it may vary from vendor to vendor, but it's usually something like best path, AS path, multipath relax, which just says relax that rule a little bit, and if the AS path lengths are the same to the same prefix, accept them both, and now you've got multipathing. So it's just sort of maybe a preview into the fact that there's a lot of small adjustments like that to be made simply around ECMP. And obviously, in a CLO topology like we're showing here, ECMP is a key to making the whole thing work well. But being able to modify sometimes default BGP behaviors is important so that it does work right.
Yeah, and as we have always said, BGP was initially designed for sparse topologies, not densely populated graphs. So data center deployment requires some adjustment to default BGP behavior. They're well known, but it's important to remember to turn on right knobs, unless your automation platform does it for you.
Yeah.
So overlay to underlay relationship. As we go forward, we will talk more and more about overlay. So in our case, EVPN. However, what's always important to remember is your next hop is always underlay route. So imagine in this data center, you run both overlay and underlay. Your overlay, in this case, BGP EVPN, in route received, next hop will be underlay. So in order to converge fast, you need to make sure your underlay converge. So just overlay isn't enough. So what you want to have really is your underlay route to go away as soon as possible if you lose link or not. Why is that? As we said, all modern implementation do next hop tracking. So when you have many routes, the same next hop, which is the case here, when your next hop disappears, your implementation will invalidate all those routes. Make sure your underlay is fast and performant in order for your overlay to converge fast.
Yeah. And just to interrupt before you go to the next bullet, there's a question that came in that said, is there a place where I can find all of these BGP data center best practices? There is an RFC that's sort of the foundation of all of this, which
7938.
Thank you. I never remember RFC. I was hoping that your memory is better than mine.
It's in my working group, so I have to.
Oh yeah, that's right. So you'd get fired if you couldn't remember the number. Yeah, so that is absolutely the first place to go to get best practices. But over the last couple of times, I've been meaning to plug a book. I've got finally remembered to bring it up on my iPad. I've only got it a digital copy, but well, let's see. Sorry, this is so maybe it's not showing up so good. There it is. BGP in the Data Center by Dinesh Dutt. One of my favorite books on exactly this topic, and I highly recommend it. And I don't know if you can see or not, up in the corner here it says Compliments of Cumulus. You can actually, I don't know if it's still available as an ebook, like I've got it here from Cumulus, but I believe it is, where you can just go and enter your contact information, and they'll give it to you for free, so you don't have to buy it on Amazon or whatever. But really good book. And Jeff, I don't know if you have other books that you like, but that's certainly one of that's the book I like to recommend for.
Yeah, so I really like Dinesh's book. They're easy to read and easy to understand and kind of entertaining. So Dinesh published 3 books in the last couple of years. One of them on BGP, another one on native cloud. He published it actually a few months ago. So do read it. Usual disclaimer, it was written with Cumulus in mind. So when you read Cisco Press books, you need to realize they have their angle. Same goes for those books. Cumulus has particular great features. Cumulus missing some others. So you might see a bit of a skew into don't use stuff we don't support.
Yeah,
if in any way diminishes value of the book, as kind of independent reader, you should understand why some angles have been taken.
Absolutely.
So next topic is the forwarding plane convergence. So convergence is the point between event happening and switches sending traffic to each other, fully restoring, so no drop. So obviously, there are more than control plane BGP convergence. There's also time that takes for route to get installed in forwarding plane. In data center, we use 2 different technologies since we have overlay and underlay. So underlay traditionally has reasonably little amount of route. So unless your data center is thousands and thousands of switches and flat IP space, which we can discuss another time. I mean, it's questionable where you could do summarization, how to reduce this number. And routes are grouped in the ECMP groups, as we said. So from forwarding plane perspective, you see this structure usually implements mtry that has number of routes that make part of ECMP group and kind of single logical exit. So in this case, there's no need to do hierarchical convergence. We use technology known as fast rehash. So if one of the routes in the ECMP group disappears, we just remove it. Some implementation do it with stickiness. So actually, you keep sending old flows into the links that were there previously and only change for the ones that failed. Some other completely rehash. So again, it's implementation dependent. However, there's no need for hierarchical data plane. What you do, you just remove failed, or you add new next hop that just appeared because there's some new route, and you keep using it. If you look at overlay, however, this is where you will see possibly millions of routes. So in all good days, we've tested some UVPN implementations with hundreds of millions of routes. So what you don't want to have is when next hop changes to download tens of millions of routes into forwarding. To give you some idea about speeds, good implementation will give you something between 50 to 100K prefixes download speed. We are talking RIP to FIP. So if you have 10 million routes and you could do 100,000 a second, do your math. In the less optimized implementations, and I mean, often you would see this in data center switches because they have less powerful ASICs and less optimized fast pass from RIP to FIP. They could do 10,000, maybe 15, 20,000. In other worse, if there's many routes in overlay, it will take seconds, if not minutes, to converge. In this case, it's important to have hierarchy in data plane. So you are not pointing to the route itself. You create an intermediate point or indirection in forwarding plane where all the routes that point towards same next hop are part of the same group. So this technology, known in Cisco world as PIC, prefix independent convergence, there are similar implementations on pretty much every vendor. Again, what it does, it removes this direct structure in forwarding where every prefix points to the next hop and create an intermediate entity where all prefixes are grouped together to point to a logical entity that is not physical next hop, but a logical next hop. So if next hop goes away, all routes associated with this next hop getting updated faster. With many routes, make sure vendor you're using actually supports this technology. Traditional vendors have been supported for quite some time. We've seen Cumulus implementation, or actually FRR implementation about 6 months ago. So they implemented the grouping in forwarding page. Make sure you understand the differences, because the surprise might be really nasty. If you run many routes and suddenly figure out that your underlay recovers in milliseconds, but it takes tens of seconds for all your overlay routes to get updated.
Right. And we've got about 2 minutes left here for wrapping up.
So to give you some preview of what we are going to discuss going forward, so we are going to discuss ECMP considerations. So as usual, there's a draft that Piotr Lopochov and myself have published, an informational document. It actually discusses and describes all the nerd knobs you need to enable and how the stuff works. So look for ECMP consideration drafts.
So there's some homework for everybody before the next time.
Yes. So with regards to PIC, there's another draft, obviously in routing working group, where else, that describes PIC implementation. It's really good work. It's informational, published mostly by Cisco people. Go read it if you want to understand how PIC exactly works. And after that, I think we will try to move more to overlay, so discuss EVPN artifacts. EVPN is multi-homing. It's a absolutely fascinating topic.
Absolutely. Okay, well, this has been, I don't know about you, Jeff, but I'm finding the 30-minute format is a lot better, because we don't feel, I'm not looking at the timer myself and going, oh my gosh, we've got all this material and we've only got 10 seconds left. It's a chance to be a little bit more relaxed about what we're talking about, take a little bit more time in our explanation. So for those of you that are listening, by all means, give us some feedback, whether you prefer the 15-minute format or the 30-minute format. We will certainly be interested in hearing what you have to say about it.
And please send your questions. As long as they're relevant topic, we'll do our best to address them, to explain why particular decisions have been taken, either in implementations or IETF. And we are looking forward to talking to you again very soon.
Absolutely. And so goodbye for this time.
Goodbye, everyone. Bye, Jeff. Talk to you soon.
See you, Jeff.
Cheers.